So the basic question behind all we did here was how can we compare different BIPV projects? And we have different use cases for that, either to compare design options in the design process or to facilitate the evaluation of different projects in a competition context like it exists in many European countries. It's also interesting to look into when we want to identify the best practice solutions we want to disseminate. And it could also give us opportunities to identify areas for improvement in existing BIPV designs. And in order to answer these questions, we developed a new analysis tool in this subtask B. And this new analysis tool was relatively early on decided to have certain features. And the ones we settled at were that it has to be multidimensional. We don't have only one single purpose of BIPV projects, but they have to fulfill a whole area of subjects. And therefore, it was split into 4 different areas: the economic performance, the energetic performance, some environmental key aspects, and then also aspects of optical and visual appearance. In addition, we decided to make this new analysis tool cross-sectional. So we're only looking at one certain step in time, either in the planning phase or in the operation phase. And we're basically looking only at how does this project perform at this point in time. So that means we're sort of disregarding reliability for now, but as Suna mentioned before, this will be covered partially at least in phase 3 of task 15. And finally, this method should be parametric. So we want to have actual numbers to all these values so that we can easily compare it. And for this, we developed 5 to 6 key performance indicators, or KPIs, per category, which can be evaluated on a grade of 1 to 5, with 5 being the best grade. And here's a list of some of all these key performance indicators in these 4 different categories. I just want to highlight a few of them, which are more easily understood maybe. And that's basically the categories where we have quantitative measures, which are the energy relevant, economic, and environmental aspects. And these were basically developed based on expert opinions from experts in task 15, but also with contributions from task 12 and task 13. And those basically represent the limits of the state of the art. If we look now into these energy relevant performance indicators, we can see here a few examples. So one of them would be the PV array energy yield in DC, or a performance ratio, or a self-sufficiency index, which describes how much of the energy consumption of the building can be fulfilled with the system. And then we developed some threshold values for the different performance indicators. And then as soon as you can calculate them for the system you're evaluating, you can then develop these values for these key performance indicators. There is one issue, however. I mentioned that only 3 of the 4 categories have actual quantitative assessment, and that is the visual appearance or KPIs. And there it's really difficult to find a way to put these values into numbers, because appearance aesthetics are naturally a very subjective area. So in the end, we settled on a semi-quantitative method for this KPI. And basically, there are 6 different values in this category. The first one we were talking about is recognizability. So can you recognize a system as PV when you look at it? In some cases, that may be wanted, or it may be unwanted. Especially in heritage areas, we often want to hide the PV component in our system so that it blends in with its surroundings. The next 2 parameters are color uniformity and glare risk. And those basically provide us some measure of how well this system looks and how well it performs in terms of fitting into its surroundings and not annoying any neighbors or other participants in this urban environment. And then we have sort of 3 KPIs for the architectural integration on 3 different levels, which are basically based on architectural terms. in order to assess these parameters, we developed some guidelines. And here I show examples for the color uniformity and the glare risk, where we basically introduced a merit and demerit system. So if this system shows some certain aspects, then it gets a positive or a negative rating, which allows us to convert these appearance metrics into something that is actually quantifiable in this rating from 1 to 5. And we then tested this within the Task 15 community during one of our task meetings in Sweden, where we could show that this visual PI intercomparison, while not perfect, still gives us a way to evaluate these parameters in a reliable semi-quantitative way. And then once you have all these KPIs, you can visualize them. And this is what we call this multidimensional evaluation matrix, which is basically the end product of this task B. And you can see here we have these 4 different areas: energy, economic, environmental, and visual performance. And each of them gives us an average performance value in their category. And that allows us to directly compare different systems with each other. As an example, I'm showing here 2 cases we looked at in the task 15 subtask B phase. The one to the left is one of the lighthouse projects that was built in Switzerland. You can see you're looking uniformly gray, and that's colored BIPV modules combined with dummy modules that basically cover the entire facade of the building. And that, of course, has some consequences for the performance of this system, because many of these modules get shaded during different times of day. They're facing non-optimal directions. The energy performance of this building is not great. On the other hand, the appearance metrics are quite positive. You have a very uniform appearance. They use satinated glass, so you have almost no glare risk. And it also fits decently well within the building and the urban environment. And then on the right side, we have a different application case, which is sort of less customized and more mass customized, which is a system in the Netherlands where a whole city quarter was outfitted with roof integrated BIPV. And this system performs much better on the economic side, but of course has to trade off some visual aspects and of course some innovativeness in its design. Another part that was covered in this subtask B was to also look at different types of building integration. So this example shows an integration of BIPV in balustrades, balconies, window blinds, and we could show that this matrix was applicable there as well. However, since we here are looking at the research project, we do not really have economic performance indicators. So that brings me to the conclusion of subtask B already. So we developed a new analysis tool to allow us to compare vastly different BIPV systems for a multitude of different purposes. It is multidimensional, it's cross-sectional, and it's parametric. But of course, during that process, we had a few challenges. One of the challenges I didn't mention before, but which is certainly still the case, is you have to obtain all the data that goes into this matrix, and that can be difficult at times. The visual evaluation, as I mentioned, we developed a semi-quantitative method. It's still not perfect, but we're getting somewhere at least. And finally, the comparability of lighthouse projects is a bit difficult. So these highly customized projects by their nature will have a higher cost due to all the customized solutions in them. And therefore, it can be quite difficult to compare those to more mass customized systems. And this work will also be presented in an article in PV Magazine, I believe, this month, and in a scientific journal early next year. So I would invite you for questions if you have any on this aspect.